Welcome to Boom, where we have
Biomechanics on our minds.
Boom.
Boom, boom, boom.
Boom, 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 boom.
Boom.
Hey everyone, we're back with more Boom. For those of you listening for the first time, I'm Melissa, the student representative for the International Society of Biomechanics and a graduate student at Stanford University.
Hi, I'm Hannah. I'm also a graduate student in bioengineering here at Stanford.
Today on the episode, we're going to be speaking with Professor Scott Delp from Stanford on open science and a little bit about women in engineering. We're going to start off again with a bit of Boom that Hannah is providing. I hear it is again on bird biomechanics, so that should be very exciting.
Yeah, Melissa, you know how birds fly in a V and sometimes one line's longer than the other? Why is that?
I don't know, Hannah. Why is that?
It's because there's more birds in that line.
Oh, no. Oh, dear. Well, is there an actual scientific explanation for this?
Well, I'm not exactly sure why more birds fly in one line, but many have suspected that the actual V formation helps birds fly with less effort. And the precise mechanics were unknown until January 2014 when a team led by Stephen Portugal at the Royal Veterinary College in the United Kingdom studied some birds and did some fun math.
Oh, I love fun math.
So basically, when a bird flies, it creates spinning loops of air behind it called vortices, and part of this vortex system pushes air upwards, also known as upwash, while the opposite side of the vortex pushes air downwards, known as, you can guess it.
Downwash?
To fly with less effort, a bird should time its flapping to press its wings through the upwash created by the bird in front of it so that it gets lifted up and can use less effort. And it wants to avoid the downwash that will push it back down. Yeah.
So how did they go about studying this?
Well, by precisely recording the spacing of the birds in formation behind a plane, they were able to time their wing beats and show that these birds actually do time their wing beats for maximum efficiency and were locating themselves in the most efficient position in their V formation that the researchers had calculate using fixed linear dynamics.
Wow, so they actually flew in an airplane next to the birds in the V formation.
In front of, yes.
And studied. Oh, that's
awesome.
And
filmed them, yeah. It was
wow,
pretty cool.
That's such a neat study. How do the birds, can they sense other birds around them, or how do they kind of know how to do this formation?
Yeah, so that part is still unknown. Perhaps the birds have some sensory abilities that we weren't aware of, or maybe they could actually do the math needed to judge the distance to the next bird and sort of count their own wing beat cycles to be in time.
Maybe the birds can help me pass quals in a couple of months with all their math skills.
I think so. You just got to go up there to train with them.
Well, thanks for the fun fact, Hannah. Now we're going to go into our interview with Professor Scott Delp.
Today we're talking with Professor Scott Delp at Stanford University. Professor Delp is the principal investigator of the Neuromuscular Biomechanics Lab and the James H. Clark Professor of Bioengineering, Mechanical Engineering, and Orthopedic Surgery, as well as the director of the National Center for Simulation and Rehabilitation Research and the Mobilized Center. He is also an ISB Fellow. Thank you for talking with us today. Would you mind first sharing a quick summary of your current research here at Stanford?
Sure, I'm happy to. I think it's great you guys are doing Boom. It sounds like an exciting project, and I'm glad to be part of it. So we study human movement, and we do that with experiments that we run on individuals who are athletes at Stanford, or individuals who are graduate students at Stanford, or individuals who have physical disabilities. We also make simulations because we can use the simulations to look inside people and assess things that we can't measure in experiments. If we want to know what the forces are in muscles or the stretchinesses of tendon when somebody's running, we can make simulations and explore those. So overarching all of this is understanding movement and enhancing movement. For athletes, trying to provide methods that reduce or prevent injuries for individuals with physical impairments, enhancing their performance so they can fully participate in society. So that's what motivates us.
Great, thank you. So we're kind of hoping to talk a little bit about open science, but before we get started on your involvement in it, could you explain a little bit about what the term open science means?
Sure. Open science is sharing your data, software, models, ideas with the community to best accelerate scientific progress. So that's in contrast to keeping things secret, which is frequently done in industry, for example, where there are billions of dollars of industrial research, but we don't see the results of that because it's kept secret. So open science is full disclosure of the scientific process and scientific products to advance science.
In 2006, your research team began working on the development of a powerful, freely available software for simulating human movement called OpenSim, where users can address fundamental issues in movement science, just as you noted, and focus on these critical areas of rehabilitation medicine, including for stroke, spinal cord injury, cerebral palsy, investigating prosthetics, orthotics, and diseases like osteoarthritis. OpenSim has been a big step in the support of open science. Is open science something you've always been passionate about?
Well, I didn't really know what open science was when I got started. When I was a PhD student, one of the things I did was I made a computer model of the lower extremity. And I spent a few years developing this and testing it. And when I started my faculty career, I thought, well, people were asking for the model, I should give it away. And I had to format it and answer their questions, but I thought, well, this would be a good thing to do. This would help other people not have to redo what I did. I got advice from others that said, no, you should keep this to yourself because it's your secret weapon, right? No one can do with your model what you can do, so you'll have an advantage of getting grants and that kind of stuff. And I thought, that's not why I got into it. I got into it so that I could advance the field, and it'd be better if more people were working on it. So I posted it on the ISB website, and it was one of my first experience with open science was just posting that and having people from around the world download the information that was that lower extremity model and begin to ask me questions. Now, that was when the internet first began. So before that, there was email, but there wasn't the World Wide Web. So it was just a year or two after the internet became in more broad use that we posted that model, and that's how I got started. It was quite rewarding, actually, to see other people who I didn't know but could take advantage of this advance their science by a few years just by starting from where I left off.
Yeah, that must have been really interesting to see how your project was able to generate new ideas with other people, and then that could even come back around and spark new ideas for your research and kind of start more of a collaborative effort in the field. What other barriers have you come across, if any, in trying to encourage or foster open science? And are there any disadvantages that you've seen?
Yeah, I guess I'll start with what are the advantages and then what the barriers and disadvantages are. So the advantages are if you create something, an engineering artifact or a scientific finding, and you make it available open source, then other people can really take advantage of that. So if you're writing a paper about it, they can read the paper, utilize your work, build on it, and cite your paper, and it really does advance science. So for me, that's a huge advantage. And as a young biomechanist, for example, if you want to have impact, that's why we're all working, right? We want to do something good in the world, and if you want to have impact, this is a way to do it. So that, for me, is a huge advantage. There are some disadvantages. It takes time. It takes time to package your work up, to make it available, to make it understandable, to document it. So that extra time you could spend on your next project, not on the documentation of your past project. People also ask a lot of questions, so that can be a disadvantage too. It takes a lot of time to support all those people. People also can find errors in your work, and you can think of that as an advantage or disadvantage. So when I made my model available, I had a license agreement where people had to report bugs to me so I could fix the model. instead, what I've seen is, that happened in some cases, but in other cases, people would go to a conference and people would have a poster about an error they found in my model that I made 12 years ago. And I was like, why didn't you just tell me? I could have fixed it. So there can be an embarrassment, like if you make all of your research methods available and others can view that level of detail, they can spot problems that may go unrevealed in a lot of scientific studies. So there's an advantage that you can actually improve the quality. And all of our computers operate on open source software. The Linux operating system, which drives many computers, is an open source project, and it would never reach the level of quality it has without hundreds of users correcting bugs and fixing them. So while it's a disadvantage that people can find errors in your work, it's an advantage that people can find errors in your work and you can fix things, and that also advances the field. I've heard from others that they're concerned about making things available open source for a few other reasons. One is that they might not get credit. So people might download their stuff, use it, and not give them credit for all the work they did. And that happens for sure. It's happened to me many times, but it doesn't really matter, because if you don't make it available, you wouldn't get credit either. So there's also people are worried about, they invent something, they create it, they put it and make it open source, and other people take it and go make money on it. And I heard that from a bunch of people. In our licenses, we allow people to do that. If somebody wants to take our models or software and commercialize it and make money on it, that's allowed. There are other licenses that only make your materials available for nonprofit research. So you can choose which you want. And people are usually pretty respectful of those license agreements. Another disadvantage people find, or at least an excuse they cite for not making their materials open source, is that they're worried about misuse. So you may have developed a piece of software or an algorithm or a model with a particular use in mind, and you may have tested it for that use. But other people may take it and misuse it. They'll use it for the wrong purpose. They don't do the same checks you did. And the fear is that will discredit your original work. And this is a legitimate concern. And we have tried to be really clear in our work about the range of applications in which we've tested our models, our software, and where we haven't. And we put the onus on any scientist using our tools that they do their own testing, they do their own validation, they be good scientists and do good science and make sure they understand the tools they're using, the range of applicability. And so that puts the onus on other people using it. Now, people will still misuse it and get incorrect answers. And so the balance has been, we make our things available, and there is some poor use of those, but there's also a lot of great use. And the scientific community has the responsibility to weed that out and see what's good science and see what's not. So that's kind of the advantages and disadvantages in my view.
Do you think that there are any types of research that may not be amenable to open science, or are there certain ones that are easier to do?
Yeah, so software and computer models make sense for open science. Mm-hmm. When you're trying to translate some technology like a medical device, it usually doesn't make sense, because if you have an invention at the university and you want to translate it out into a product, that's usually going to require investors to take a risk on your technology, and usually it will take tens of millions of dollars at least to get that basic invention out into a human trial, maybe hundreds of millions of dollars. And in that case, the better translation technology is a patent. So instead of copywritten software that's freely available, you may patent something. And by its nature, patent excludes people from practicing the art that you teach in your patent. And that's required for investors to know they have an advantage and will be able to make profit if the invention turns out to be a good thing. So open source, open science is not always the best way to have impact, but it's an important way. But there are other pathways like patents for biomedical technology that are really important and a really worthy path to pursue. It all depends on how you're trying to achieve impact.
how do you think that the view of open science has changed since you were in graduate school, and how do you see it changing in the next 10 years or so?
I never heard the words open science when I was in graduate school, so I don't know if there was a view on it. There were probably a few people. It's become much more of a big thing now. And I think it's slowly evolving where people recognize the value as scientists to make their tools available. So we started this website, SimTK, Simulation Technology, about 10 years ago so that we could disseminate our research results. And at that point, we were just building a tool for ourselves to share the software and models. But now there are 50,000 users of that site and almost 1,000 projects that share their research results. So that's a big change from not having heard of it to thousands of projects sharing data. About half of those 1,000 are in the area of biomechanics. So people might have a big project or a small project. It can be just a part of a PhD thesis. It can be one paper, but they have research results that they want to share. And that has really changed pretty dramatically, even over the last 10 years.
That's amazing that shift has come and that you've been a huge driver of it. And I think we as students are wondering if we should feel obligated or some sort of responsibility to encourage this atmosphere of open science. And if so, how might we support it to develop our own careers in this field of biomechanics?
Yeah, I think the best way students can support it is by participating. If you have a research result for which it makes sense to share your data, for example. So, Hannah, if you're collecting data on Parkinson's disease patients, you may, at the end of a project, once you publish the paper, want to share the kinematic data that you've collected so people could try other algorithms on it. Yeah. So that would require, though, that you de-identify all that data to make sure it's allowed with the IRB, and that's a lot of extra work, but it really can, I know you get into the field because you want to have an effect on people who have disabilities or have Parkinson's disease, and so if that's what's motivating you, then this is one good way to have impact. Now, it doesn't always make sense to do it. Sometimes you're just going to write a paper and there's no associated data where it would make sense. Right. And you don't always have to do it, but where it makes sense, then I think it's a good thing to do. And it's worth the time. For sure, we've seen my own students, when they do make research results available to the scientific community as open source products, then their impact is much greater. You can see it. We've done an analysis within my own lab when there is and isn't sharing. The impact of the papers for which there is sharing is much greater. It's statistically significantly greater. And we normalized for, it's a single lab and journal impact factor and all that kind of stuff. So it does make a difference.
It'd be interesting to think of that being, if you can do that type of analysis, that being some kind of criteria to hold labs to have some level of collaborative nature. Yeah, I like there's the carrots and sticks, right? Some journals will say, we're not going to publish your paper, like the PLOS journals will not publish your paper unless you make your research results available. So PLOS is the Public Library of Science. So the PLOS journals require that. So that's kind of a stick. The carrot is, if you do, then you'll have some upside. Right. So I think both are good. And so I'm excited about what PLOS has done. Yeah. Having these open science journals is just great, because it's frustrating that we may spend an incredible effort to write a grant, to get money from the federal government, to come in here, to do the research. And that might take years of analysis and writing, and then volunteer editors hone our paper, and after, say, 5 or 6 years, we might get a publication, and then publishers hide that behind a firewall, and if you don't pay them, you can't see it, even though it was a government-funded project. So PLOS kind of turned that all around, and I'm grateful that they have. And I think we need more of that and more openness in journals, and for them to revise the way in which their business model works so that the publicly funded efforts can have the biggest impact.
So I guess this is all really great, but what if you're a student that wants to be involved in open science, you want your work to be open science, but maybe the professor or who you're working with isn't necessarily a supporter or doesn't feel the same way about open science. Do you have any advice on navigating around that?
Yeah, so that's tricky. Not having support from your faculty mentor is a tricky issue on lots of fronts.
Absolutely.
I think in this case, and in most cases in general, to have a good scientific debate with your faculty mentor to say, look, here's why I want to do it, here's what's motivating me, here's the upsides, here are the risks, here's the downsides, here's how I've evaluated it. Show him or her some data and say, this is what's driving my decision. If your faculty advisor is a good scientist, they'll listen to data and be open-minded to change their point of view. So I would go in with data.
Yeah. Makes sense as a scientist. We're going to take a quick break from the interview with Scott to talk about a necessary evil in research, which is failure. Hannah did a really awesome project on failure, and so she's going to talk about that a little bit more, and then we're going to share some of our failures with you.
Yeah, so I took a class this past quarter, and we were wondering how students interact with this necessary but hidden part of research. And you see a lot of professors walking around, and they seem to have it all together. You look at their resume, they've gotten every fellowship and research position that they've ever applied to, but what went into that? There was a lot of hard work and actually a lot of failure and things that didn't work before they got to the place that they're at now. So we put up a wall, Hall of Fail specifically, in one of the engineering buildings here on campus. And we seeded the wall with some stories of research failures written on sticky notes that we had experienced in our lives, and just left a simple prompt on the wall that said, share a research fail, with a bunch of sticky notes and pens for other people to leave their own stories of failure. And what we found is that we got a lot of responses from people talking about little fails on the scales of setting their projects back a week or so, all the way up to 1 to 2 year long setbacks from various failures. And professors received this really well. They liked the idea, and we got a lot of comments that said, from people that said, oh, I could fill up this whole board. And I know I feel that way too sometimes.
So what were some of the fails that people put up?
Let's see. One person said, I realized I'd been using the wrong equation to calculate stuff the whole time. And that got a couple plus ones.
Yeah. I like the one that says sneezed while feeding stem cells. That sounds like a problem. ...
Contaminated.
Oh, the fire one.
Oh, I set fire to my bench was another one. And it was funny, there were a lot of research fails that centered around this sort of just a mistake that could have happened because of the universe, but everyone tended to put it on themselves. Like someone's laptop got stolen and they said it was their fault that they didn't back up the data, but it wasn't really their fault that the laptop got stolen. So it's interesting to see how people perceive failure and put themselves responsible.
Yeah, I think that's a really good point. What's one of your failures?
One of mine was that I dropped a $300 round bottom flask on my first day of being in a research lab, and that was really fun. And I offered to pay for it, but everyone...
They didn't make you pay for it?
No, it was okay.
I've had a couple fails recently, but they haven't been as much researchy as just kind of klutzy. The problem is this is Scott's interview, so I'm not sure if he's going to be listening to this. He'll probably never let me buy anything nice again. But last week I spilled an entire smoothie on my laptop that I had just gotten from the research lab. And I managed to get it off. The laptop's still working, but the smoothie got under the keys, so it's a little crunchy when I'm typing, which is kind of annoying. And then I also managed to lose the department card in IKEA when I was buying a new desk.
The best place to lose something.
Literally the worst place to lose a credit card is IKEA. So after the 3 hour just walking through IKEA, another 3 hours of searching through IKEA. Luckily we found it. I also proceeded to accidentally use the department card to buy a 12-pack of Rudolph the Red-Nosed Reindeer noses this weekend so I'll have to be returning those.
Do you want to press the keyboard so that they can hear the crunch?
I was like, can you?
Can you hear it?
That's some nice crunching.
Mark Zuckerberg once said, "The greatest successes come from having the freedom to fail," and I think that kind of sums up our work really well, that we are at a very privileged place to be able to fail so often and so much and actually grow from it. So it's really important.
Yeah, I completely agree, and I think that project was really awesome, and it's just a good point to remember that it's okay to fail, and the best thing you can do is just learn from it and grow. And one quote that I like to use often is always aim to fail, because then if you do fail, you've succeeded, and if you don't fail, it means that you succeeded. So really all the time you're succeeding. So definitely something to consider.
The best part is that quote is said by none other than Melissa Boswell.
I did come up with that quote, and now I'm sharing the quote that I came up with, so.
I live by it too, every day.
So now we're going to head back into the interview with Scott Delp. He has a couple more words to say on women in engineering, which was really cool to talk about with him. So I hope you enjoy the rest of the interview. So we kind of want to shift gears for a little bit. Knowing that you're also a strong supporter of women in the field of engineering, we were kind of wondering what experiences have motivated you to become active in this area.
Yeah, I'd say the big thing that motivated me was just being a mentor to female engineering students and seeing what they were experiencing as their careers advanced, both in graduate school and outside in industry and especially in academics. So I'm motivated to support my students and understand their issues and help them find a good pathway. That's my job. That's what we do as professors. And so I had a number of female students that faced difficulties that my male students hadn't faced. So that alerted me to the issues, and just in the context of supporting my students, I became a supporter of this general issue. Mainly in academics, because that's where I play. I haven't had much of an influence in industry, but in academics I've seen the issues and tried to have an influence here at Stanford and also through my students at their institutions.
So we talked about how open science has kind of evolved over the years. How do you think some of these issues regarding women in engineering may have changed over the years, and what do you think the most current difficulties women are facing right now in engineering?
Yeah, I'd say when I first started my faculty career, I had student advisees that were facing overt discrimination and statements that were incorrect and derogatory about the women's capabilities in engineering, where male professors, advisors were suggesting that women didn't go into engineering because they didn't have the capability, which is obviously false and but still demoralizing. And I don't see examples of that anymore. I haven't seen any examples of that in a few years. What issue remains is that in academic hiring, there's discrimination against women by men and by women. It's proven, and there's a number of possible causes, and the way out of that is not exactly clear. So for me, that's the current key issue. Is it's not overt. It's kind of, and it's not intentional even. They're just intrinsic biases in the hiring process, including how letters are written, how CVs are evaluated, how interviews are conducted, the level of preparation that candidates are given or not. And those practices need to evolve as scientific evidence for how to do it fairly and in a way that supports men and women equally emerge. So that's the current issue. And the good news about that is that's now becoming open. Like, people understand this, their educational materials, their scientific studies. And so when it's covered, it's hard to make change. When it's open, you can begin to make change. The challenge now is what changes should be made to actually make it fair, and how can we open doors in a way that is supportive of women and avoids the the side effect that might be, okay, you got this job because you were treated as a special category, which is also a problematic part of the hiring process. So it's a good challenge. It's worth facing. It's worth changing what the demographics are in academia, because that makes it a stronger enterprise. More diversity is obviously better. That's also proven, and gender diversity is a key part of that. So for me, is trying to improve the academic environment here at Stanford, and for me to try to support my students who are at other institutions, that's what's really gotten me motivated. And I have seen a lot of positive change, and there's still a long way to go.
Yeah, thank you. I think it's just great to continue to talk about it and think about how we can keep improving this. So now we have our final question of the interview, which we're doing for all Boom interviews, which is, what are you currently most excited about in the field of biomechanics?
That's a great question. I'm excited about a few things. One of the things I'm excited about is moving biomechanics out of the lab and into the world. So for me as a biomechanist, when everybody started carrying accelerometers in their pockets by way of their smartphones, that was a real opportunity. So most of the biomechanics studies we do have 10 or 50 or maybe 100 people. We just finished a study in which we had 6 million participants because they all had a cell phone app that enabled us to track their movement and behaviors in 64 different countries. So that changes the scale at which we can do biomechanics. So thinking about studies that we can do in thousands of people or hundreds of thousands of people or even millions of people opens the door for biomechanics to have really great impact on public health. Also, moving out of the lab, the whole movement of developing field-based measurements with IMUs, for example. We still make very high quality measurements in the lab, and we do it every day, but we'd like to be able to make assessments out on the track or in rehab at home or out in the real world, because we can see, for example, clinical gains are made in the clinic when someone's with their physical therapist or occupational therapist, but we don't know how that translates home. So being able to make measurements in the home for people who have physical impairments or out in the field for people who are trying to optimize athletic performance is a big challenge and something that's very exciting, and it's going to transform the field of biomechanics from being primarily lab-based to making the whole world our lab. So we've been trying to build open source tools to enable that to be done in an accurate way. The challenge is, now that everyone can make measurements with their iPhone or with inexpensive IMUs or with a Kinect at home, there's lots of bad measurements and lots of bad data and lots of erroneous conclusions. So we want to make this happen in a way that's scientifically legitimate and with the most sophisticated engineering tools. So I'm excited about trying to help with that transformation from in-lab to out in the wild experiments in biomechanics. I'm also excited about taking basic things from the lab and turning them into products that people can use. So I'm motivated, and I got motivated for biomechanics to try to have impact on patients, and that usually isn't done in the lab. Usually it's done after there's some discovery in the lab. Someone told me, you never really cure anybody by writing a paper. So the figuring out how to do that is exciting to me, and I do that a lot of times if a student has an invention and they're going to graduate and they want to translate their device or technology out in the field. I'll help them start a company to figure out how to translate that, to raise money, to start the company, to try things on patients. And that's fun and exciting too, because it never goes the way you think it's going to go. There's usually a big twist that happens, and seeing that, and it's hard to anticipate, but it's a pretty fun ride. Yeah. And if people stay focused on doing good science, serving people who have the need for this new technology, usually you can figure out a good path through that. So that translational technology is exciting to me as well.
Sounds like there's a lot of exciting places for the field to go in the next, X amount of years, and it'll be really cool, I think, to kind of there's a possibility to merge those two exciting things you mentioned and having that kind of closed loop of feedback between real biomechanics in the world and having translational devices that can
Totally
respond
agree.
to them.
Yeah. Thank you for talking with us. I think kind of the theme I kept seeing through this was just accelerating scientific progress, and it's clear you're really passionate about that.
You guys are the future of biomechanics, so I'm always feel honored to be able to work with bright students who want to make a difference, and hopefully you'll do that, and the people listening to your podcast will do it. So thanks for doing Boom.
Yeah, thank you.
Thank you. Boom on 3.
Boom! Okay, all right, sorry.
You're too excited.
Yeah, I'm fine.
Biomechanics is too exciting.
Okay. Boom on 3. 1, 2, 3.
Boom!
That wraps up our interview with Professor Scott Delp. As a reminder, National Biomechanics Day is on April 11th this year. So if you're interested in participating in National Biomechanics Day, you can check out the website at nationalbiomechanicsday.asbweb.org.
It's really fun.
And you can follow us on Twitter at ISBiomechanics and follow the International Society of Biomechanics on Facebook.
So thanks for listening. If you guys have any ideas for topics or professors you'd like to interview or any personal fails that you would like to share, please send them to isb.studentrepresentative@gmail.com and we'll be happy to hear from you. Boom on 3. 1, 2,
Boom!
3.
Boom!
Come on, you said on 3.
Everyone goes after 3.
Yeah, it's like rock,
You guys-
paper, scissors.
Be clear, man.